chapter is all about energy and work. Okay, energy and work. The stuff you guys use so much of and do so much of. You do so much work and you use so much energy, right? All the time. When you walk upstairs, when you walk up the stairs in the morning, you're doing work because you're exerting energy. So we're going to look at some theorems this chapter which relate work and energy. If a person is a weightlifter and they're lifting something above their head, they're doing work because they're exerting energy to do that. They're gaining potential energy in the weight by lifting it up. And then they bring it back down. They're exerting a force over a certain distance, so they're doing work. So this whole chapter 5 is about work and energy. Mathematically speaking, it's a pretty easy chapter. Okay? There's not much when it comes to that. It's really interesting because we're going to learn this chapter that there are other ways to solve some of our projectile motion problems, which are easier using energy methods. So remember how we would always do VIX, VIY, and use all our kinematics? Certain problems in that situation can be solved using energy. Only certain ones, though. And it's a lot easier. Okay, so when we get to those, I'll make sure we emphasize that. So when it comes to like the midterm exam, if I give you a question for a free response, you could solve some of them using kinematics or using energy methods. Either one is fine. Okay, if you're more comfortable with one or the other, it doesn't matter. The objectives for this section, work and energy, are to define and understand scientific work. Okay, identify when work is being performed, and calculate the net work as a result of several different forces. Several different forces. So, who thinks, let's see, what's a good example to start this with?
Your feet right now are dancing. You're dancing crazy.
I'm trying to think of a simple example of something. What if we take, alright, let's take this water bottle for example. Maybe it's a weight. Okay? So Luke's in the gym doing his curls. Well, you don't do curls at home, right?
Oh my!
Basically, you're not doing curls.
No.
Alright, so you're in the gym for some reason. Alright, somebody's doing overhead lifts, whatever it is. And they have the object here.
Right here, you know.
Now, if I were to go like this and lift the weight up and come back down, okay, versus going like this, what's the difference between those two? And be careful. Okay, be careful here. It's kind of a trick question I'm starting you off with, to be honest. So, what's the difference between going up like this versus going up like this? What's the difference?
When you're like going up like this, you are exerting energy up and then still like enough energy in order to like hold it up still. But when you, the second one, you like exert energy, and then it's more like you're letting that exert the energy that brings you down.
The way you're putting it is good, yes. So she's saying when you go faster up and quickly, you're kind of letting gravity pull it back down. But when you go up slowly, you're controlling the motion, right? You're controlling the motion. So what else? What else?
When you go up faster, you're using more energy.
Okay, when you go up faster, you're using more energy. Okay? I'm just taking opinions. I'll go over what it is.
I think you use more energy when you go up more
Yeah.
slowly.
Oh, sorry,
Yeah,
that's what I meant.
And when you bring it back, down, you use it more longer.
Okay? Alright. Believe it or not, neither of those things are true, even though I know, right? I know. I'll explain. So, here's the interesting part. In energy, and the reason they weren't true, you're saying is because of the term energy. If you had used the word power, we would use it differently. But you actually exert the same amount of energy doing this as doing this. The energy is the same. The amount of power you produce is different though. Because energy, we're going to see this chapter, and this is where there's misconceptions, because naturally you would say energy, right? That would be the term you would use. But energy-wise, energy is not related to the time. The time it takes has nothing to do with energy. Okay, again, the time it takes to do an operation is not energy, but power. Power is the rate at which energy is expended. So, for example, here, if I go like this versus going like this, the quicker one is actually more power than going slowly. Okay, than going slowly. We know, those who exercise know, that when you go with the controlled motion, it's actually better for you because you're developing your muscles better. Okay? That is better by far. But you exert more power doing this than you do doing this. But believe it or not, they are the exact same amount of energy. They are the exact same amount of energy. Yeah?
When is energy like power times time?
So we're going to see that energy is, power times time. Well, power is defined as energy over time.
Energy was
Yeah, it's the exact same thing if you solve P. Yep. Very good, James. Good notice there. So let's start with the definition of work to begin. Okay, that was just a misconception I wanted to clear up. So work is defined as the product of the component of force along the direction of displacement and the magnitude of the displacement. So write it down for a moment and then I'll explain a little bit more. It's on the board, but work is the product of the component of force along the direction of displacement and the magnitude of the displacement. So, for example, if I were to pull on this garbage can, let's start right here. If I were to pull the garbage can with a horizontal force, I'm pulling in the direction of displacement. Literally, my force is pulling this way, my displacement is this way, and that's the example for 0 degrees. But I wrote the word component. Who remembers what component means? We've been doing a lot with components with our angles and stuff.
Like a part of something?
Yeah, a part of something. So if I pull at an angle now, is the Fy or the Fx in the direction of motion?
Both.
It's only moving this way. I heard the right answer, but I was just answering this question. Yeah, so again, if I pull at an angle, and Fy is up, right, we know, because I'm pulling up technically, and I'm pulling out this way with Fx. Is Fx or Fy in the direction of motion? Fx is. And how do we always find Fx?
E times cosine beta.
Good. Take a look. F cosine theta. So technically, this equation is really this. Now, the reason I didn't put x for displacement, I put d, because I said the magnitude of the displacement, which is really what term? What term? What term? Not displacement, but something else. Distance. Remember, the magnitude of displacement is distance. If I said this, remember from the beginning of the year, what's my displacement if I walk 3 feet this way, in your opinion? -3 for my displacement, right? What's my displacement going this way? Positive 3 or whatever the number is, right? But either way, what's my distance if I do this? What's my distance if I do this?
9.
So either way, the distance is always 9.
3 feet that way, 3 feet that way.
So I meant starting is 3, come back to the beginning, and then it's 3 this way, right? So either way, distance is the absolute value of our displacement. Okay, distance is our absolute value. So in these problems, we're really doing the x component of the force times the distance. Okay, but I'm not going to write Fx because what if I'm lifting an object up off the ground? Now the direction of motion is vertical, right? So I would be using Fy in that case. You follow what I'm saying?
Yes.
Okay?
What happens in a situation where, like, I don't know, you've moved like 9 feet and then gone back like 6? I'm actually using distance as
9 plus 6.
so I'm using total. Okay.
If I move this way, 9 feet, that's 9 feet in distance. I don't care about displacement anymore for these examples. Then I walk back 5 feet. So the distance would be a total of 9 plus 5, 14 feet. Okay? So for these problems, we are looking at the actual movement, not the beginning and the end difference, right? Remember we talked about how I could take this crazy path and end up in the beginning, there's no displacement. But we're looking at the distance traveled, the path along that curve for these problems. Now, here's the thing. We're always going to use cosine theta in these problems. We're always going to use cosine theta in these problems. But theta is going to be the angle between the force and the direction of motion. Remember how in the last few examples and with inclined planes and with projectile motion, theta was always the force and the horizontal. Remember, this was always the angle. I'll draw it on the board. This was the force, and this was always theta. It was always the angle between the force and the horizontal. Now, for work, theta is the angle between the force and the direction of motion. So again, I could technically pull on this remote at an angle, and it could move up, but I'm still pulling at an angle. So now theta would be between here because it's moving upward. So imagine I'm pulling on an object, it's right here, but the object is moving vertically. It's in like a vertical, say it's in a vertical rack. You can only move vertically, but you're pulling at an angle. It moves up and down. So now for this example, since it's moving up and down, we would use that as theta right there and not this one over here. So what you want to write down is that theta is the angle between the applied force and the direction of motion. Theta is the angle between the applied force and the direction of motion. This avoids us having to use sine and cosine. We can always use FD cosine theta. FD cosine theta will always work for this. Okay?
We don't use sine.
So for work, for these examples, we're not going to be using sine. Okay, we're not going to be using sine for these examples.
Direction of motion.
The angle between the applied force and the direction of motion.
Wait, I don't understand why it's so loud.
Why it's still what? All right, here we go. Ready? Has anybody ever been to the gym where they have those squat racks that are on riders?
Yeah.
So, okay, first of all, a squat is when you put a barbell over your back and you just do a squat, right, for your legs. They have some of them where there's a barbell in a little shaft or a groove, and it slides up and down, and it can only move vertically. Now, imagine the barbell was at the bottom. So the barbell's at the bottom, but it can only move up and down. If I apply a force at an angle, right, to lift it up, it's only going to move up and down, isn't it? So I can still apply force at an angle, and it's going to move up and down. That's what I'm getting at here with this example. So if you apply force at an angle, but it's moving up and down, this is your theta. If I apply force at an angle on this table, though, which way is the table moving? Horizontally. So we go back to the other theta that we had a minute ago.
So would the force be your arms?
The force is whatever you're applying, your arm, sure, in that case. James.
And the only thing you need that measurement for is to calculate the component that's moving.
That's acting along that direction.
Yes.
Exactly. So if I were to pull horizontally, there's no theta anymore. It's acting all horizontally. So technically it would be cosine of 0. But you guys haven't learned about this yet. Cosine of 0 is just 1. Believe it or not. Which is weird to think about. You'll learn more about math this year. Cosine of 0 is 1. You will. Stop. Cosine of 0 happens to be 1. So if you acted and you pulled only horizontally, the angle would be 0. So the cosine theta would not even apply to the problem. You would just do force times your distance. Okay?
Dude, why did you say that we won't use sine? Just
Because we are going to make sure that we know that the angle is always between the applied force and the direction of motion. Remember how if the angle was here, okay, if the angle was here and we wanted to find the y component, we would use sine in the past. But now the angle is here. Whenever the angle is between these two, you're always using cosine. Just like in the last chapter. Remember the angle was between these two here? We used cosine. But when the angle was between these two, we had to use sine because this was the angle we had. But now we have this angle here. Let me give you some proofs for that. Okay, I'll show you why. Here. If you had, say this angle was 60. Okay? This would make this angle
30.
Now, if you wanted to find the y component of this force, in the past, what have we done? We said that Fx would be, let's call the force 10, okay? It would be 10 cosine 60, and Fy would be 10 sine 60. Agreed? That's what we've done in the past. And that works. That is true. Now, instead of using sine of 60, I'm telling you guys, we could always use cosine from now on, but when we're moving vertically, we should use the other angle. Well, what is this angle? 30. So do me a favor. Go to your calculator. Find out what 10 sine 60 is. And then compare it to 10 cosine 30.
Same.
Yes, the same.
You try it. Okay, so do it this way instead afterwards. Okay, try it with the cosine instead of the sine and use the angle that's between them of 30. They should be equal. It should be 8.66, right? Because sine of 60 is 0.866 times 10. Just move the decimal. It's a common angle, you'll realize. Trust me, it's not anything miraculous. You'll learn in math that sine 60 and cosine 30 are square root of 3 over 2. which is 0.866. It just happens a lot. That's why I know the number. Okay? So for these problems, for work problems, we're always going to use cosine theta. Okay, we're always going to use cosine theta. But we need to remember for work problems that theta is the angle between the applied force and the direction of motion. Before we go on, let's take a look at our units. Units of force are newtons. Units of distance are meters, which means it's Newton times meter. Newton times meter happens to be a joule. Okay, a joule. A joule. 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 It's not Yule, joule. Let's take a look at an example. Did you really or no? Yeah. Yeah. Interesting. Write down your givens. Write down what you know. Write down your givens.
Sorry, homies.
What are your givens?
Distance is 12.
All right, distance, good. Not displacement in these problems, but distance is 12.
475.
D plus 12.
Just 12.
Okay? James.
I can write FP too.
Yeah, yep. FP is fine, force pulled. And actually we should. Let's write FP. Thanks, James. Because we're going to look at friction in a moment, how friction can do work also. That would be FF. So FP is 75, theta is 60, D is 12 meters. All you have to do here is plug into your formula. That's it. Okay? All you need to do is plug into your formula. This is a pretty basic example. In a moment we'll look at one that's a little more complicated. So work equals FD cos theta gotta be kidding. Come on. Cosine of 60 is 1/2, just to help you if you don't have a calculator. So you can replace that with a half if you like. 450 you got? Check? What do you got?
5 is 60 to 2.5. Not right.
Check your mode. Is it in degree or radian? Okay, then you might have made a mistake somewhere, but it's not. Others, what do you get for work?
I got 450.
I agree, good.
What?
Aaron, you fix it?
Oh yeah, I typed in a 6 instead of 5.
Gotcha. Folks, relax. Relax. So again, a problem like this is quite simple. Okay, this one is very simple. Let's look at one that's a little bit more complex than just this. Okay? And before we'll do that with this problem.
Not the sweater. That's what
We love your sweater.
It's so cute. Rudy Pebble.
All right.
Taste the rainbow.
So we got. Can I get a reader for this, please? Get a reader. Sorry. Folks, hold on. Sorry. Before you begin, guys, stop. Okay.
What would the angle theta be if the force is the horizontal force being directed this way in the opposite direction?
What do we got for this? Think about it for a moment. Okay. Imagine that this desk is moving this way. Which way does friction act if the desk is moving this way? So that would be an example of this, right? Opposite direction. What's the angle between motion this way and friction force this way? What is that angle? 180. 180. Again, here's my force. Here's my friction force. Or here's my direction of motion. Here's my friction force. The angle here is 180, the full angle. Okay? So, Let's discuss. Let's discuss this. So the object is here. It's being pulled this way with some force of pull, but friction is acting against the motion. So if we were looking at the angle between the direction of motion and friction, well, here's motion. Ready? I'm going to draw motion with a dotted black line. That's the direction of motion. That's the way we're moving. So the angle between friction and this is 180. Please go to your calculator. Type in cosine of 180. Tell me what you get.
-1.
-1. So the work done by friction will be? Not -1, but just in general.
Oh, the distance.
Backwards.
Julian? Negative. Because remember, guys, go back, think for a moment, ready? Our equation is FE cosine theta. F will have a value, the force of friction. D, the distance it traveled, will have a value. But cosine of 180 will always be -1. So whenever you're looking at the work done by friction, you're looking at a loss of energy, which makes sense. Think about it. What does friction do to you? It slows you down. It decreases your energy. You don't know this yet, or you might have known this. We haven't gone over it though. Kinetic energy is motion energy, right? When you're moving. So what is stopping you from moving when you do this? Friction. It's applying energy in the other direction in a sense. So that's why the angle theta makes sense as 180. Because the work done by friction is always going to be negative. You're losing energy due to friction. You're losing energy due to friction.
How did Michael Jackson do this?
How did he do his moonwalk? He applied a force pushing him this way with one foot, and then and then friction slowed him down as he went back. I don't know how to do a moonwalk. Weird. But you got the idea? He pushes back, and friction is what's slowing him down as he does it.
Must have also had to be on a really smooth floor too.
Low mu k. Low mu k. Yeah, that's how I think all the time. It sounds weird, but when you have right. If you have a smooth surface, I'm always like, it's a low mu k or low mu s. But it's the truth. That's what it is, really, in scientific lines.
Be a real conversation starter.
Well, I was out at Home Depot getting some supplies last night with my uncle, and we were at Home Depot getting supplies. We were talking about their like, the push carts that you want to put like a lot of lumber on, like not a normal shopping cart, but like those things. All four wheels are free moving. They're not like locked. So those things kind of like go everywhere. And he's actually, my uncle's not that big of a person. He's pushing one of them, and he's pushing it, and as he's trying to turn the corner, it starts to like careen off into the side, and in my mind, I'm thinking this. I'm like, well, there's a lot of inertia. There's nothing slowing it down, so it's just sliding down. And like that's what I thought about. I don't know. I mean, whatever. All right, let's move on.
Related to
So here, to give you examples, take a look at the board. Guys, you need to relax a little today. Come on. Look at the board here. This object, this car is moving to the right. It is definitely moving to the right. It says that the distance is to the right in all examples. But on the right-hand side, the person's hand is helping it move to the right. It's pulling up here on the top to the right. So there's positive work. It's pulling it. It's helping it. Here it's pushing it along. It's helping it. But if it's moving to the right and you're pulling back on it, aren't you slowing it down? Like friction? So this hand is acting like friction here and here. So this is an example of negative work. So when the force that you are looking at is in the direction of motion, work is positive. That's the right-hand side. When the force you're looking at is in the direction of motion, it is positive work. When it's not, it is negative work. When it's not, it is negative work.
Is that why we drive on the right side of the street?
No. That's funny, Lisa. I like that.
No, I wasn't.
Can I, wait, so anytime there's any friction in the opposite direction, it's going to be negative?
Friction's always negative. This is always negative. Unless you're talking about friction between a tire and a road that's propelling you forward. Because that friction actually pushes you forward. That's how that works. A little different. Okay? Last example. A student pushes a 20 Newton desk with a horizontal force of 12 newtons, a distance of 24 meters. Okay? So I'm pushing it 24 meters. Or a student, whomever. Assume the coefficient of kinetic friction between the desk and the floor is 0.2. How much work is being done by the student on the desk? So what kind of work is that going to be? Horizontal or positive, because it's horizontal in that direction. How much work is being done by the floor on the desk?
Negative.
Because that's what force?
Friction.
Force of friction by the floor. And then what is the net work done on the desk? What is the net work? What do you think we're going to do to those two numbers we get? Add them for net, right? So we'll get a positive work, we'll get a negative work for part B, put them together to get the net work. Do part A on your own first. Please draw a diagram or list your givens or something here.
So would theta be 180?
Yes.
Wait.
What do you mean?
For part A, theta is not 180. For part A, I'm pushing in the same direction it's moving. So theta is what? 0.
Oh.
For part A, again, let me go over this again. If I push this desk horizontally that way, the desk is moving that way and I'm pushing that way. So our vectors line up on each other. There's no angle at all. It's just going to be 0 for the first part. For part B with friction, we'll see how it's going to be that 180 we were talking about.
Is it the same if you like pull something straight up vertically?
Yeah, if I push something straight upward, if it's moving upward and I'm pushing straight upward, the theta is also 0, yes. Okay?
Wait, were you doing AB2 to like your weight is like 12?
Yeah, so are we interested in the weight in part A? What are we interested in part A? The
The force.
Horizontal.
FP, good. The force, the distance, good.
Distance and theta.
So part A we have I'm still going to write cosine theta even though cosine of 0 is 1. Cosine of 0 is 1. Cosine of 0 is 1. Cosine of 0 is 1.
Cosine of 0 is 1.
Good.
But there is no S on 0.
There is a pole. The pole is 12 newtons. The distance is 24 meters. The cosine of 0 is just 1.
So there.
Okay? So we get a number.
Yeah, I swear. You
24 times 10 is 240. 24 times 2 is 48. 240 and 48 is 288. You can do it that way. Okay? So, the work done is positive here. Now, the part with friction next is we have to figure out. We're not given the force of friction in this problem. But who remembers what the definition of force of friction is from the last test? Mu Fn. We have mu. It's 0.2. Right? We do have Fn though. If we have Fg and it's in balance, it's in equilibrium, what is it? Yeah, it's the same thing. Okay?
20 times 9.81?
No. We have the weight. We don't have mass. Guys, remember. And a lot of you made the mistake on your test yesterday. That's too much work. Let me just point this out. Give me a sec. I'll point out what I'm saying. Here's our object. Here's Fg. Here's Fn. There's no vertical motion, so sum of the force is equal to 0. So negative Fg plus Fn is equal to 0, right? So this is a state of equilibrium. So these are equal and opposite. Therefore, Fn is the same as the weight of the object. Remember, this is the one circumstance where you can say they're equal. We're given the weight of the object, so you don't have to find the mass. Don't go back and find the mass and then multiply by g, because it's circumventing the problem. You'd be dividing by 9.81, but then multiplying by 9.81. Okay? So, let me one second. So force of friction that we're going to use, because we're going to find the work done by friction, is going to be this, times cosine of 180. But remember, force of friction is mu k times Fn. But Fn is Fg in this problem. Okay, and that's the problem we're going to use here. You're going to get an answer of negative 96 joules. And then for part C, add 288 and negative 96. Okay? Over the weekend, your homework is very simple. There are 4 problems from this section to look at. Okay, that's it for 5-1. I told you these are quick sections. They're easy ones. Spend some time this weekend. Some of them have vertical motion. Make sure you understand thetas between the distance and the force applied.